Very fine, yes.
Yeah, wait a minute. Let me organize it. Yeah, 1 minute, please. Okay, well, so hello everybody. So first of all, I would like to thank organizers, so which brings together all of us for this memorial workshop. Thank you, Larissa. Thank you, Vladimir. I'm happy, but at the same time, it's a high honor for me to collaborate with Yuri Gaididei for about 20 years. Our collaboration was mainly in the field of nanomagnetism. It resulted in very fruitful projects. Altogether, we have about 60 joint papers. Besides, what I'm sure is extremely important, this collaboration stimulated an appearance of a new generation of young researchers. During this talk, I will try to sketch the contribution of Yuri to two fields of magnetism: nonlinear dynamics of magnetic vortices in nanomagnets and to the curvilinear magnetism. I will also briefly present the story about work with young researchers. I start with the activity of flat magnets. For the first time, I met Yuri in 2000 in Dresden. There was a workshop and seminar on vortices and solitons organized by Franz Mertens and Arnold Kasevich. Here you can see the web page of this workshop. It is still accessible through the website of Max Planck Institute. Several collaborators of Yuri who are present today were also in this event. I mentioned Franz Mertens, Avad Saxena, Peter Christiansen. During that workshop, Yuri presented a talk about internal dynamics of breezes and vortices, and namely internal dynamics and nonlinear phenomena was the first subject of our future collaboration. I would also like to mention the talk by Tilcam Peter during that workshop, the PhD student by Franz Mertens. Together with Franz and Yuri, they constructed a theory of noise-induced switching phenomena in the vortex dynamics, where internal nonlinear dynamics of magnets was crucial. And these words, internal dynamics and nonlinear phenomena, became a keynote of our collaboration. From 1999, I started to visit Bayreuth University every year to collaborate with Franz Mertens. And Bayreuth University was the place where we started to collaborate with Yuri Gaididei, who started to visit Bayreuth much earlier than me. And we definitely saw and discussed in Bayreuth every visit. However, we start to collaborate a bit later in 2002, 20 years ago. I remember our fruitful discussions with Yuri Gaididei, Franz Mertens, and Jean-Guy Caputa in Bayreuth, which resulted in my first joint paper with Yuri. The first project was about the vortex dynamics in Heisenberg magnets. It was the part of PhD project by Juan Pablo Zagorodny, the first author of this paper. Excited by a rotated in-plane magnetic field, the vortex starts to move and reach some limit cycle. It was a surprise that the frequency of the vortex orbit motion was lower than the driving frequency. And to describe this effect, it was necessary to take into account internal degrees of freedom of vortex core, coupled to this, some translational motion. 1 year later, we applied this for nanodots. Probably it was it was a first joint paper on nanomagnets. Yuri didn't like having his picture taken. That is why some of photos were made during some official events like here. In June 2005, Jean-Guy Caputa organized a conference on nonlinear science dedicated to 50 years after famous Fermi-Pascal-Urban problem. It was really impressed that Yuri participated in so many very different projects. The spectrum and comprehensiveness of his experience was really amazing. We started to collaborate with Yuri through France Mertens. And next several years, we collaborated mainly in Bayreuth. We met in Bayreuth University to work, but also during weekends to discuss. In 2006, Vladimir Kravchuk started collaborate with us as a PhD student, you can see here. We worked at that time mainly on the problem of nonlinear vortex dynamics, including some switching phenomena. And let me take some words about that activity. One of important question which people discussed a lot at that time was a problem how to switch the vortex polarity, which means the vortex core magnetization. That problem appeared because the vortex was considered as an information carrier. The simplest way to change the vortex polarity is to apply a DC perpendicular field, like here in this sketch. And namely, such kind of switching was firstly observed experimentally. In order to realize such a switching, one has to apply very strong fields about saturation field, which means about 1 Tesla. And together with Vladimir Kravchuk, we describe such switching phenomena. Another possibility was proposed in 2006, and it was the resonance mechanism under the action of a field pulse of about just few milliteslas. One can switch a vortex core during a nanoseconds and even faster. And later, very similar results were realized for different combination, linear polarized fields, rotating fields, different electric currents. And at the time, we intensively worked in this subject and made our contributions to the theory of many of switching effects. And I would like to tell a few words about one of these projects, namely the current-induced switching in heterostructure. In 2006, I was a Humboldt researcher at Bayreuth University. I remember how Yuri paid my attention to what is called now spin-torque nano oscillator. At that time, there was already few publications about spin-torque switching of homogeneously magnetized sample. Yuri asked the question whether we can switch the vortex. I mentioned this because besides a very broad experience, Yuri also had a very advanced scientific intuition. The physical picture of this switching includes an excitation of internal gyroscopic mode, its nonlinear resonance, and appearance of new objects, the vortex-anti-vortex pair. And you can see here by citations of this work that the forecast proposed by Yuri was a very wise decision. The spin-torque switching of the vortex polarity became very popular. Gyroscopic modes can be excited not only by currents, but also by rotating magnetic fields, like in these publications. Similar picture takes place if one excites high modes. Here you can see how high magnon modes can be excited, how they appear, vortex, anti-vortex pair, and so on. All nonlinear effects are very well described using the central manifold approach, which we elaborated together with Yuri, and this approach developed a series of papers at that time. The next activity I would like to mention is about vortex-antivortex crystals generated by a spin current. If we consider the same spin torque nano oscillator but change the direction of the current, the dynamics results in the vortex-antivortex crystal generation. There is a modulation instability of the saturation state. The crystal phase appears just below the saturation state. And Yuri suggested the way how to describe this instability. You can see from this figure that if we decrease the current, there appear the state which is characterized by a short range magnetic order, the so-called fluid phase of liquid state. If we decrease the count more, they appear some other states, gas states, some more specific symmetrical states. The details will be presented by Alexei Volkov, who made most of this hard work during his PhD. When we studied the switching of the vortex polarity, we realized that depending on parameters, the dynamics of such system can be regular or sometimes chaotic. It was always interesting to dive together with Yuri in new phenomena. In particular, we studied properties of Bloch points, which is a topological singularity of magnetic distribution. We constructed several models which describe three-dimensional effects in vortex statics and dynamics. All projects I mentioned of this slide were part of the PhD study of Alexander Pilipovsky. And now I would like to tell about other direction, which is known now as a curvilinear magnetism. Firstly, we worked with complex structures in two-dimensional magnets. Later, we worked with thin nanomagnets. And the following step was to study what new topological effects appear in thick magnets. And after that, the next step was to consider non-flat magnets. And this activity was mainly stimulated by our collaboration with experimental group of Denis Makarov, which was initiated in 2010. The group of Denis Makarov made pioneered experiments in magnetism of chord geometries. Our first step was to consider the vortex not in a disk, but in a spherical shell. We know that in case of disk, the streamlines of magnetization have azimuthal directions. Instead of that, the streamlines of vortex on a sphere have additional turning, which depends on the vortex polarity. And there appears a coupling between the well-localized perpendicular magnetization of the vortex, the so-called vortex polarity, and with the delocalized in-surface magnetization far from the vortex core, which is the vortex chirality, the so-called polarity-chirality coupling. In magnetic caps available by experiments of Denis Makarov group, there appear different magnetization textures like vortex, onion, is the axial textures, and we describe these textures and phase transitions analytically, and which agrees very well with experiments by a group of Makarov. An essential breakthrough in the understanding of curvilinear effects was dated by 2013. At that time, we visited Denis Makarov in the framework of joint DFG project. It was a month full of very exciting discussions. We learned a lot of new subjects and methods, not only physical one. In particular, we studied differential geometry. Besides, we cross-worked with an exchange energy. Every day, together with Yuri and Volodymyr, we had brainstorms. It was very exciting time, which I recollect with a great pleasure. Finally, we proposed a theory of Covalinear magnetism, which is now well established and confirmed. According to this approach, the covalinear geometry of magnetic shells leads to the appearance of geometry-governed anisotropy and geometry-governed Delaschitsky-Maria interaction, which is responsible for the symmetry break. The last one has a similar form to well-known interfacial Delaschitsky-Maria interaction with consequences like helical structures and skirmion crystals. An important message is that there exists one more mechanism, the geometrical one, for the Delaschitsky-Maria interaction. I do not like big words, but other people say that this paper was a cornerstone to the theory of covalinear magnetism. To conclude this story, I would like to mention that to that moment, we did not work systematically with curved system. That is why we tried to use results known in different condensed matter and soft matter system and realized that all of them were incomplete. They were based on a classical book dated by 80s, which considered only tangential field. And this is not the case of magnetism. Previously, the correct descriptions of curvilinear magnetic shells were obtained only in specific cases, like here with cylindrical shells by the group of Pedro and Deres, and for spherical shells by our group. Starting from that time, we actively work, and we are still working in the field of covalinear magnetism. I will not discuss numerous results in this field. This will be presented in talks by members of our team, Volodymyr Kravchuk, Alexei Volkov, Alexander Pilipovsky, Konstantin Ryashov today. I limit this part of my talk by mentioning just few examples. Probably the first review of curvature effects in magnetism is dated by 2016. At the same time, application to the shapeable magnetoelectronics was well developed by the group of Denis Makarov, and it will be presented in talk by Denis today. The Magnetism Roadmap 2017 presented novel materials which properties determined by curved geometry. And later, the Magnetism Roadmap 2020 selected the curvilinear magnetism as a novel prospective topic. Here you can see this screenshot from the Scopus profile of Yuri. It is worth to admit that Yuri worked in very different fields with a lot of people. Here you can see that there were 158 co-authors. And nevertheless, the magnetic activity, namely the curvilinear magnetism, was a very important part. You see that the top two publications from this Scopus profile are the review paper about curvilinear magnetism I mentioned, and the PRL on curvature effects. I would like to mention also the last paper by Yuri. Yuri did not see the journal version, but only the archive version of this paper. This is a paper about the non-local chiral symmetry breaking. In that paper, in order to understand the non-local physics of curved magnetic fields, it was useful to describe magnetostatic interaction by three fiction charges: tangential charge, geometrical charge, and surface charge. The tangential charge is determined by tangential magnetization components only. It coincides with the volume charge in flat magnets. The geometrical charge is determined by the local characteristic of the curved surface, its mean curvature, and properties of magnetic texture. Thus, it couples the magnetic subsystem with the curvilinear geometry. All these three charges do interact pairwise with a non-trivial contribution to the energy. An interesting physical consequence is the possibility of non-local chiral symmetry breaking effect. It introduces a chirality in intrinsically a chiral material. A micromagnetic framework of Covalent magnetism provides an interplay between the symmetry of magnetic interactions, the curvature, and the magnetic textures. And the last part of my talk is about Rhythm team. I think it's very important part of activity aimed to grow young generation of researchers. What does the Rhythm mean? This acronym means the research in theory of magnetism. It is an informal group of several theoreticians originally from two Ukrainian institutions, Institute for Theoretical Physics and Kyiv University. There is no exact date of appearance of this team. The story goes back to 2002 when we started to collaborate with Yuri. This collaboration was enriched by Vladimir Kravchuk, who joined in 2006, later in 2009 by Alexander Pilipovsky and Alexei Volkov. Starting from 2009, the team has regularly enhanced by new researchers. Konstantin Yershov in 2013, Artem Tomila and Alexander Zayats in 2018, and Elizaveta Borisenko in 2019. Here you can see also the former members of our team. Part of them are present in the workshop. In particular, I saw in the Zoom list the participation of Mykola Svoika. More than 10 years ago, we started to organize regular research seminars. Part of our meetings have had a journal club format. Part of them were about current research discussions. However, every time there was an enthusiastic atmosphere, numerous hot but kind discussions, brainstorms, and so on. We organized our seminars, meetings, both at the Institute for Theoretical Physics and the Radio Physics Department of University. Today, we continue the development of directions and problems initiated during this very, very fruitful collaboration with Yuri Gaididei. And I would like to finish my talk with this web page of review on Curvilinear Magnetism, which appeared just 2 weeks ago. This review is dedicated to the memory of Yuri. So thank you very much.
Thank you very much, Denis, for this very interesting talk with a lot of highlights. And for me, it was very nice to see these magnetic structures that Yuri told us a little bit about, but not in very much detail. But it's really fascinating, I think. We have time for some questions.
I have a question. I don't see how to raise my hand.
Yeah, but that's okay.
Denis, this is Larissa speaking. Thank you very much for your interesting talk, and also to Avat Saxena. I just did not want to interfere. Well, first of all, I want to thank the team of young people who collaborated with Yuri and who continue to recollect him, who published papers even after his death, and who remember Yuri. That's very important for elder generation, for Yuri's family. But a question is very brief for my education. You mentioned, Tom, cylinder shell or sphere shell. You mean that you take into account the thickness of the structure? Why shell? Why not a tube, for instance? Sorry, thank you.
Yeah, exactly. Okay, thank you. Thank you, Marisa, for kind words and for your questions. So wait a minute to find this. Yeah, you're right. So, okay. So probably it started from the question of terminology. So, but exactly. So first we constructed the theory of very thin shell. So we started from the surface and extended it a bit. So it was really a shell. And we constructed, so the terminology is used for typically for object, so for magnetic systems, very thin in comparison with, for example, magnetic lengths. And in this case, it will be possible to treat it using exchange interaction only. So, but if you are a thicker object, so definitely they appear the non-local effects driven by magnetostatics, and in this case it will be really tube. Yeah. So just to distinguish these objects. Yeah. Thank you.
Thank you. Thank you.
Do we have more questions? Okay, then I think we should thank the speaker again for this.
Yeah, thank you very much.
Thank you very much.